This is homework 24. We'll be doing problem 5 from section 6.4 and problems 1 and 3 from section 6.5. The first one reads, determine the orientation of the neutral axis and calculate the maximum stresses at the outside corners of the cross-section due to some load P. Data for the beam is as follows. We can also use Appendix F for the dimensions and properties of the beam. So I'm going to pull up Appendix F properties for my W8 by 21 flange, and it's knowing that it's asking for the neutral axis, I'm going to be using this equation from the book. However, this equation is a more general equation. It's assuming that we don't have this pretty symmetrical beam. It has a I sub yz, or the product of inertia, and since we do have this pretty symmetrical beam, we know our product of inertia is 0. So I can just simplify it to this equation here by removing all of the parts with the I sub yz. We don't have any information for moments, but we do have a load P. So if I solve for my moments, and I'm going to go through my moment sub y for you, and you can do the same for sub z. If I go along some distance L across my load, I have some P that's acting on it, and the P acting perpendicular to my y-axis is the portion that's multiplied by sine alpha, because if we look at our image here, it's alpha away from y, given the laws of geometry. One could argue that the distance of the moment is only L halves. However, it doesn't really matter since our L's are going to cancel out anyways, as will our P, and even our sine and cosine are going to be turning into a tangent. And this equation here that it simplifies into is what it will simplify to every time, so long as I sub yz is 0, which it will be in every case for this homework assignment. And we can just start with this, and as long as we have our I sub z and I sub y, which we have from our table, we can plug and chug, do some arctangents for our beta, and get our answer of 72.5 degrees. Next, it wants to know the stresses at the outside corners. So our stress equation for any given point on a beam is this equation. We have a z and a y as our coordinate system to whatever point we're going to, and since we have 4 corners, I'm going to try to just quickly get all of that information. So for my A, I'm going to go for A first. I'm going to go down some y distance, which is going to be half of the depth, and it's of course negative because we're going down. And conveniently, I just realized that I have also found my y coordinate for my B, and if I negate that, that is also the magnitude to my D and my E. Anyways, moving to our Z direction, we're going in the positive direction by half of the width, and I can, since it's symmetric and everything, I can use that exact same magnitude and then having negative where it's necessary. I can plug all of this information in, knowing where my W and D come from the table, and I get the following stresses. The first one reads that a beam with a channel section is subjected to a bending moment, having its vector at an angle theta from the z-axis. Determine the orientation of the neutral axis and calculate the maximum tensile and compressive stresses in the beam using the following data. So we have this channel here, and it's asking for some neutral axis. If I'm arbitrarily drawing this right now because I don't know where the neutral axis is, but I do have this other equation, and it requires some beta and some theta. So if I arbitrarily draw this line, with the beta connecting the line to my z, because that's also where theta is connecting a z to my moment, then this equation becomes valid. I have my theta, but I don't have my inertias. However, thanks to the appendix, and the appendix labels my y and my z-axis as such, I can copy that data into this equation, solve for beta by just doing an arctangent, and plug and chug. Next, it asks for the maximum stresses in tensile and compression. So my equation for a stress at some location across the face is this equation. But this will give us some stress at any location, and we want the z and the y coordinates that specifically relate to our tensile and compression locations. And although it might be obvious where the two locations are, it might not be obvious which one is compression and which one is tension. So just real quick, I'm just going to fill them in. These are our two locations. They're the locations because they are the furthest from a line, and although if you do it real quick, you can say, oh, they're the furthest from the line that I drew earlier, but recall that the line that I drew was arbitrary. So we actually have to redraw our line with our 83.07 degrees, which is going to actually be a little bit steeper than how I have it drawn. And then the furthest location from that line is going to be these points. But as for which one's compressive and which one is in tension, that's just something that you're going to have to figure out a way that works for you. For me, what I do is if I put my hand in kind of a clench, so if I'm clenching my hands, like if I'm angry and I'm going to punch something, then but I have my thumb extended, so my fingers are closed but my thumb is extended. I can put my thumb in the direction of the moment and my palm away from me. Or yeah, if I have my palm away from me and my thumb in the direction of the moment, then the side where my fingers are is my compression, and the side where my wrist is my tension. That's the way I do it. That is not the only way to do it. There's also plenty of conceptual ways you can do it. It doesn't matter, as long as you figure out some method you can use to figure out where your compression and tension is, that's good. So anyways, we need some y and z coordinate for each one. There isn't a coordinate system here, except with respect to, or rather, our coordinate system is respect to the centroid. So for my y, I'm going to go down by half of the height, or in other words, half of the depth of, say, our web, even though it includes the thicknesses of our phalanges, and then divide by 2, or sorry, yeah, half of that. And then for z, it's just going to be that c value. And then we're going to do the same thing for compression, getting our d, w, and c values straight from our appendix table. Then we can plug and chug, and we have our stresses. Next up, an angle section with equal legs is subjected to a bending moment having its vector directed along the 1-1 axis, as shown. Determine the orientation of the neutral axis and calculate the maximum tensile and compressive stresses in our being with the following information as given and using information from Appendix F. So, because we're finding our neutral axis, we know we're going to be using this equation, and we also know that we have some information available to us in the appendix. So, using axis 1-1 and axis 2-2, we can find our eyes and plug those in, but notice on our figure here, our theta is 0 because our m is in line with 1-1. If we plug in 0, we're going to get that beta is 0. This is I think it's the only case where this equation does not work, because we're told that we can choose an arbitrary axis to measure our moment from, because ideally we have some coordinate system and we can have a moment in any direction and then solve for our neutral axis. The only case that I'm aware of where this is not the case is when our moment is in the same direction as our axis. And since we can't move our moment around, we're going to have to move our axis. So, still looking at our appendix information, it does have on the far right this teeny tiny bit of information about an axis 3-3, which, as labeled in the appendix, but I don't have shown here, is this orientation right here, which I'm labeling as y. So we have an r min for that and nothing else. We kind of just have to go off that information. And then since our axes have to be perpendicular, of course, this is where my other axis is going to be, which I'm labeling as my z direction. So Based on this, now we can draw an arbitrary neutral axis and have a phi labeled a theta, where theta is 45 degrees. And we need to solve for I sub z and I sub y so that we can find our beta. Now, we're going to go digging far back in our brains to something that we learned and used in homework number 10. There was something called the radii of gyration. And the radii of gyration is r equals the square root of I over a, and it's determined from the inertia equals distance squared times the derivative of your area. It's the same thing. It's literally just inertia, but this time we're solving it for our I, where our radii of gyration, the minimum, is given to us in this table. So that's what we're looking at here when we have r min, and we're using that information to solve for our I sub y. Then, to solve for our I sub z, this is another equation that I am not so sure if it's explicitly stated in the textbook. I didn't see this. However, we're using this method, is that the sum of inertias will always be the same no matter what orientation you have. So if I sub z plus I sub y equals I sub 1-1 plus I sub 2-2, then I can solve for my I sub z with my I sub y that I just have, and getting my 1 and 2 axes from the table. Now, if you're thinking, where on earth did this equation come from? This is because it follows the same laws as Mohr's circle does with stress and our shearing and stuff like that. And you may recall that the sum of two normal stresses at some orientation will equal the sum of the two normal stresses at some other orientation. And that's the same thing happening here, because they both follow the rules of Mohr's circle. Not super important. You don't have to dive into deep conceptual understanding of that, but that's what I'm using here to find my two i's. And now that we have all this information, I can plug it all in and solve for my beta, which is 75.5 degrees. Next, it wants my maximum compressive and tensile stresses. So first, we need my equation, and I have my I sub y's, my m's, I sub z, my thetas. I just need my coordinates. And again, if I put my thumb, and this is the method that I use to find my compressive and tension, if I put my thumb where my moment is and my palm away from my face, then my fingers are the compressive side and my wrist is the tensile side. So I'm going to first start finding my coordinates for my tensile. And notice we're not using the old coordinate system of 1-1 and 2-2, which is what information is given to us as. So I have to somehow convert my C value from this horizontal distance, which is given to me in the table, to this crooked distance. Luckily, because it's just a very simple 45-degree angle, I can use trig, or I can use Pythagorean's theorem, whatever I want, just to find out that, oh, my maximum tensile stress is going to be at a c times root 2 distance away in the positive direction, because z is to the left here, or downwards and to the left, and it doesn't go up or down from the y-axis, so that's just simply my 0 for height for my y when I'm going to be solving for sigma. Next, I'm going to be solving for my max compression, which, if you look at that, it can look kind of intimidating. However, we're going to make it as simple as possible. I know this information right here. I have my height from the table. Sorry, we don't actually have it from the table, but we know that it's 6 inches just because of the type of beam that we have. But we still need, I want to know the horizontal distance from my centroid along my z and my vertical distance from my y. So I'm just going to start with my vertical here, because that doesn't seem too difficult for me. If I am taking my h and I'm going to project it onto my y, again we have this right triangle, and this time it will be my h divided by root 2. You can use Pythagorean's theorem if you want to prove that to yourself, and if you don't believe it. And then for my horizontal distance, it's going to be going in the negative direction, but it's also shifted left a bit. And the left amount that it shifted, conveniently, we've already solved for it, it's c times root 2. So I can say my coordinate system for compression max is c root 2 minus h over root 2, comma, h over root 2. And that's what we plug and chug, and we get these answers. So we've seen neutral axes before. Previously, we were using the first moment of inertia, q, which the whole process was we would say there is some location where above that location, the q is equal to the q below that location, and that whole axis there is the neutral axis. However, if we look at a beam and we have some location that we look above and below, we'll notice that at any orientation, so long as it's fixed about that point, the q is in fact staying the same as the value of the q below, like the top and the bottom one. So this is where this equation comes in, because sometimes our moment doesn't come in at some angle of symmetry, because if it comes in at an angle of symmetry, that's when we could just use the old method that we did and not have to worry about some beta angle. I hope this was helpful, and good luck on your homework.